Welcome to this short video by Practical Stats. The title is How Many Observations Are Censored Data Worth? My name is Dennis Helsel and I'll be presenting the video today. So the topics of this short webinar or video are three. First, don't give up when there's a high percent of non-detects. Second, don't make up rules for data with high detection limits. Let the data decide whether an observation is useful or not. And finally, learn how to compute the worth of censored observations. If I have a data set with 25 detected values and 5 non-detects, how many data points do I have? If you'd like more information on methods for data with non-detects, our online course, Nondetects and Data Analysis, is located at our training site, practicalstats.teachable.com, and you can take a full, it's at least one semester of material that demonstrate and teach you how to use methods for data with non-detects without substituting any numbers in for those non-detects, without what I call fabricating data. So for today, first, don't give up with a high percent of non-detects. Here's a data set, TCE concentrations in groundwater. There's approximately 80% of the data overall that are censored. There were 5 reporting limits, 1, 2, 3, 4, and 5 micrograms per liter. What we do see is that for the low density residential areas, there are no values above the highest detection limit of 5 micrograms per liter. For the medium density residential area, we have about 10% of the data above 5 micrograms per liter. And with the high density residential group, we have about 20% of the data above 5. And so the question is, do the TCE distributions differ among the 3 land use groups? There's a lot of confusion over the value of non-detects. What is the value of all of those values below 5? In older guidance documents, such as the RCRA guidance in 1989, it said to put in a half the detection limit when there were fewer than 15% non-detects. So somehow 15% was a magic number. A little bit later, about 10 years later, the Guidance for Data Quality Assessment, Practical Methods for Data Analysis, said to substitute in 1/2 the detection limit when again there were 15% non-detects. So this number was latched onto, I believe, without any science behind it, and said, well, if it's not too many non-detects, then we'll just stick in a number. And what they have not done is to decide, well, what detection limits were those non-detects at? And were those detection limits low, in which case they had a lot of data, a lot of information in that data? Or were those detection limits relatively high, in which case there was not anywhere near as much data in those data? About 10 years later, things had advanced even more. The Environmental Statistics Manual of the Army Corps of Engineers in 2008 said to use the test of proportions, which is the same as a contingency table test, for data with 50 to 90% non-detects. And that's a pretty good recommendation. I would still say that's a worthwhile thing to do. It's not the only thing that you can do, but it's a worthwhile thing to do. But somehow this 50 to 90% rule came along. And in 2009, the unified guidance from EPA said to use nonparametric methods when they were greater than 50% non-detects. It would be nice to know what value those non-detects were. What information content do they have? What you don't want to do is what the early guidance said, to substitute 1/2 the detection limit or any other fraction of the detection limit. If you want to know why, there's another video on this page that will tell you why not substitute 1/2 the detection limit for non-detects. But the short answer is when you do that, and I've done that here, and run an analysis of variance on those 3 groups, and none of the tests, no matter what you substitute in, finds a difference. That's because substitution is fabrication. You're making up data for all of this 80% of the data that are below 5. There are, in fact, differences that can be shown between these 3 groups. See that other video if you're more interested in that, but there are better methods for censored data. And so this is a nonparametric method that allows multiple detection limits. It's a censored data method. It's the types of methods that are taught in our Nondetects and data analysis course. So the command is send one way. Just quickly here, the test statistic looks pretty big and the p-value is quite small, 0.0003, rounding it. So it tells us that these three groups do in fact differ. They have a different CDF, cumulative distribution function. They have a different set of percentiles. This is done with something called a Pareto test. And you'd find out more of what that kind of test is in the course. It also, you can do pairwise comparisons, so the low versus the medium group are not different, but the high versus the low and the high versus the medium are different. So this percent of data above 5 is part of the signal here that is contributing to this difference. All of this is done without substituting 1/2 or any other fraction for data with nondetects. Second, don't make up arbitrary rules for data with high detection limits. So some organizations have realized, and this is correct, that data that have high detection limits distorts the results if you then stick in 1/2 the detection limit. So this is a really bad practice. So for detected values in the range of about 0.5 to 6, for example, so that's where your detects are, with the highest detect being at 6, and all of a sudden you have a detection limit of less than 50, probably because one sample was diluted 10 times because of matrix effects or something like that. If you stick in 1/2 the detection, that one observation has 25, and that's going to dominate the computation of the mean, distorting it, inflating it. The mean will probably be far above 6, the highest value that is a detect. The standard deviation will probably be huge. So you don't want to do this. So people have set arbitrary thresholds above which they throw out those nondetects that are really high in their detection limits. And I've typically seen over the years, if there are 2 to 3 times the highest detected value, then throw them away. But I've also seen lower rules. And again, I don't think there's any science behind any of these that say if it's about 80% of the highest detected value, throw it out. So the data above those thresholds are deleted. The non-detect data are deleted. Here's something that does have science behind it. Here's a plot of a CDF, a cumulative distribution function, the set of percentiles, and the step functions here in blue are the data. It's jumping up at every observation. And then the smooth curve is the fitted distribution. This is a normal distribution here. So what if you had a non-detect that was higher than all the detects, like a less than 50? And here is the highest detected value. Looks like it's about 6. It's up at the 99th percentile, let's say. All that is known for a less than 50 is that it's somewhere between the 0th percentile and the 100th percentile. In other words, it's somewhere in the data set, but you have absolutely no idea where, because you cannot say that less than 50 is below or above any of the observations that are in the data set. You don't know whether it's below or above 2. You don't know whether it's below or above 4. You don't know whether it's below or above 6. It really adds no information to this cumulative distribution function. And this is a picture of the information content in the data. Based on science, you can say that if your detection limit is higher than the highest of all the detects in that data set, then it has 0 information content for that data set. The information in nondetects is contained in the percentiles that detection limit represents in the data set. So if the detection limit is at the 10th percentile down low, there's a lot of information. If the detection limit's up at the 90th percentile, then there's only a small amount of information. But if the detection limit is higher than all the detected values, there's no way to assign a percentile to the detection limit. Data like that can be thrown out. Now, censored data methods recognize this. So if you're doing something like the Kaplan-Meier procedure or maximum likelihood methods, and if you want to know more about those, you can take a look at some of the webinars on our training site. those methods correctly evaluate this. You don't have to throw the high non-detects away. The procedure will just see that those have no information, and so there's nothing there to use. They give them their appropriate weight of 0. You don't have to cull them out of the data set, which is nice. So there's no need, if you use these good methods for censored data, there's no need for arbitrary rules about throwing away high non-detects, as long as you're using censored data methods. All right, now the main topic. What's the worth of censored observations? And this is based on a presentation given by Dr. Brenda Gillespie at the University of Michigan last year at the American Statistical Association. And so here's the URL. You can go to get the PowerPoint slides of her presentation. When the question is regression or doing things with maximum likelihood methods, like trying to estimate a mean, those methods use the percent of the observations that are below each detection limit to determine the percentile that detection limit represents, and then that information is used to compute the eventual slope and intercept or mean. So for a smaller percent of observations below a detection limit, in other words, if the detection limit is down low, like at the 5th or the 10th percentile, you have more information, because you can see that those non-detects are less than 95 or 90% of the data in the data set. And so that comparative information is important, and it's used in maximum likelihood methods. When the question is, do groups differ in value, or other tests that are using nonparametric methods, a smaller percent of the observations below the detection limit again produces more information, because you can directly compare it to other observations. If you have a less than 3 in your data set and you have detected 10s in your data set, you can say that when you go from a less than 3 to a 10, you've gone up. That's an increase, and that's the kind of information that nonparametric tests use. So again, the lower the detection limit, the smaller percent of observations below it, and the larger probability of exceeding that detection limit. That kind of information is available. So here's just a picture of the CDF again with 3 cutoffs. Let's suppose your detection limit was at about 1.7. That's at the 10th percentile. You've got a 90% probability of exceeding that. You know that that's at the low end, and you can use that information. If you're at the median, approximately at the median, at about 2.9 here, then the probability of exceedance is 50%, the exceedance of that detection limit, and you've still got about half the information you would if that was not less than 2.9. if you had some numerical value there. So you'd know where to put it on the CDF. But since it is a non-detect and it's at the median, you've got about 50% of the information left. And if you're up at the 80th percentile, you've got about 20% of the information left. You can compare that less than 3.7 to the data above that detects above 3.7. But you really can't say where that less than 3.7 is in the lower 80% of the data set, where it is along the CDF. It's somewhere from down low up to that 80th percentile, but you don't know where. So here's an example of a data set that we use in the course, and this is thiomethoxam concentrations in pollen, and there are 4 categories here of where or when that was collected, and you can see from the box plots it looks like things are going down from group 1 to group 4. And there's a good portion of the data, especially in the 3rd and 4th groups, that is below the detection limit of 0.05. So what's the net worth of those observations? What's my sample size for this data set? Overall, there were 204 observations. 87 of those were less than a detection limit, and I believe there was only one detection limit here at 0.05. The number of detected then is simply 117. You can compute, based on the percentiles of the detection limit, the equivalent number of observations in those censored data. So there were 87 censored values. It's equivalent to about 50 observations. So you've got a percent of the worth of those censored observations as 50 over 87. And that results in a sample size equivalent of, if everything was detected, of 167 observations. So there's still a lot of information in these censored data. And especially when you see a pattern like this and the percent of censored data increases as you go from 1 to 2 to 3 to 4, then you can see that pattern of it going down. So the worth of a censored observation depends on the question you're asking. If you're asking a fairly simple question, then censored data can often answer that question more easily. So for example, if you're comparing data to a standard, that's an either-or situation. It's either below the standard or it's above the standard. So the censored data have a different worth, and it's a binary worth. In other words, it's going to be either 0 or 1. If you had a less than 0.05, say for thiomethoxam, and the standard was 1, I'm just making that up, then the observation is below the standard, and so the worth of that observation is 1, because you can clearly say it's below the standard of 1. Just as you could if you had a detected 0.18, that's also below the standard. But on the other hand, if your detection limit was above the standard, so it's a less than 5, you can't say that the observation was less than the standard. You can't say the observation is greater than the standard. You don't know. And so the worth of that observation then becomes 0. So to summarize, don't give up when there's a high percent of nondetects. There are many, many kind of procedures, especially if you're using good methods, censored data methods, that you can find differences between groups at 80% censoring, as this example showed earlier. So don't have arbitrary cutoffs of percent censoring above 60% or 70% or whatever number you're going to pick out of the air, that above that it's not worth doing anything. There's still a lot of usefulness in censored data, even at maybe 80%, 90% if you use good methods. Second, don't make up rules for throwing out high nondetects, data with high detection limits. Let the data decide that. They can do that if you use censored data methods. They recognize that either they have 20% information, so keep them and they'll add a little bit to the data, or that they have 0% information, so they're not going to be used. So let the data decide. And third, learn how to compute the worth of censored observations. The output that I showed earlier was with a command from our course called equivalent n that gives you the equivalent number of observations you have with your collection of censored data, and that depends on the percentiles that the detection limits have within the data set. And that worth is something that changes depending on the question that you're asking. If you're comparing things to a standard, you have a 0, 1. It's just as good as a detected value if it's below the standard, and you can say that. Or it's not much help at all because you cannot say it's either below or above the standard. Our next webinar will be on August 18th at 11 a.m. Mountain Time. I'm going to do my best to live stream it, and the webinar will be the topic of what can be done with nondetects. It's the state of the stats address. And so I'm going to go over an overview of everything you can now do for data with nondetects, including estimating summary statistics, comparing to standards, regression, trend analysis, and more. And you can do all of those things without substituting 1/2 the detection limit. So if you know people that have no idea of what can be done without sticking in a number like 1/2 the detection limit, I'd ask you to ask them to join us. It'll be about for an hour. And the link to the live stream will be on our website probably about a month before the talk, so mid-July, something like that. It will also be sent out in our August newsletter. So you can sign up if you're not already for our newsletter and get the announcement and the description of the content emailed to you. If you're not in North American time zones, that's fine. This will be recorded and it will be on our training site, which is practicalstats.teachable.com. Also, you will find there previous webinars that have been recorded. And there's many that deal with nondetects. They all have a logo that looks like a less than one or something like that. So you can listen to those if you have not heard them already, and let others know about them. So thank you for viewing today. The methods for nondetects that we talk about in the class, many of them are in a book that I published in 2012, Statistics for Censored Environmental Data using Minitab and R. For today, the opinions of this webinar are my own and don't represent those of anyone else. And if you have questions about the material or any of our courses, get in touch. You can email me here or go to our website, practicalstats.com. Thank you for viewing.